including questions, I suppose. All right, I will try. You stop me if you. I can skip some slides, so.
5 minutes to the end.
Thanks. So thank you very much for the organizer to inviting me to give you a kind of status report, I would say, of the Rubin LSST project. So Rubin, as many of you know probably, it is large survey space and time. I am almost sure that you have already seen these pictures. So they have been made public in the 23rd of June. And this is the first image that have been made public. And this is a huge sample of pixels. So you cannot have a correct view just looking at one picture. You have really to dive into the picture and to go to make a zoom, very, very strong zoom to see all the potential of these pictures. But okay, this is for the wide public. Okay, so this is the picture of the telescope that I have taken in past July. So here you have the main telescope. And here you see a telescope that looks bigger because just a perspective, that's an auxiliary telescope. I will say a few words about this telescope. And this is the inside, this small telescope. And this is the control room. Okay, so that's just to show you that LSST is alive and working, starting to work. And I started the business in LSST 20 years ago, so in 2005, before the project was accepted, long before, because we had to do a lot of things in amount of the project. For example, the mirror had to be built before the acceptation of the program. So this is the design, and 20 years later, at last, we see the real telescope and the real camera. Okay, in a few figures, I would say that the main number that you could keep in mind is 10 to the 10, because the final catalog of the LSST will be about 10 to the 10 galaxies, 10 to the 10 stars, and that's typically the number that you have to keep in mind. So the optical telescope is 8.4 meter diameter. It has a smaller effective aperture because the secondary mirror is quite large. So you have an annulus instead of an uniform surface. So the camera is huge. It's just 3.2 gigapixels, and the field of view is 3.5 degrees, 7 times the size of the moon, of the full moon. And it is equipped with a 6 wideband filters. So from near UV to near infrared. And the purpose is to go to the limit magnitude of 27.5 after 10 years co-addition of the objects. So I said to you, the final catalog should have of the order of 10 to the 10 galaxies and 10 to the 10 stars. Well, a database, blah, blah, blah. And then for the cosmology, we should do weak lensing up to a redshift of 3, and the expectation is to have 1 million of supernovae, 1A, but it's probably not, that's just a discovery. It's probably not the number of correctly measured with a nice light curve would be much slower than this number. Okay, so we expect also 10 million transients, 10 million alerts transients during a night. And this is a sociology, so there are now more than 2,000 scientists which are involved in the world, with 50% in the States. And there are 3 countries, you say, Chile and France, because France is a co-builder since the very beginning. So we have big parts of the LSST that have been built in France. For example, the filter exchange system, also the readout electronics of the CCDs, and also we have a lot of activity in calibration for the auxiliary telescope. And also in France, half of the computing and half of the catalog will be computed in France. So which is something really consequent. So it's this at all. In terms of consolidated budget, it's more or less 10% of the total budget of the LSST, which is not negligible. Okay, so thanks to this activity, Chile is the host country, so these three countries will have privileged access to all the data. So this is the focal plane. So it's 70 centimeter diameter, and here it's made of I think 20 or 21 or 23 rafts. The raft is a group of 3 times 3 CCD. And this is this kind of raft that has been used in the preliminary stage of the LSST with what we call the commissioning camera. So I will say a few words about this. So we have almost 200 CCDs in the field, which are 4,000 times 4,000 pixels. And well, so they are one of the most important things is that the readout of these CCDs is highly parallelized. So all the camera is read in 3 seconds only. So 3.2 gigapixels just acquired in only 3 seconds. So there, the site quality was selected also considering this distribution of the seeing locally on the mountain. And also another important aspect, just because we want really to have the maximum of time on sky, not with shutter closed. So one very important property is that the telescope is able to point in every direction of the sky, changing completely the direction in less than 1 minute. So it's typically 39 seconds to position to go in any other position. So this is also an important aspect. This is the global throughput. So here I show the four wideband filters, and you have many things that enters in the instrument throughput. First, you have the telescope transmission with the transmission of the mirrors and of the lenses. And you multiply this by the filter transmission, and you multiply by the quantum efficiency of the detector, and you get these dotted curves. So one curve per filter, and then you have to multiply all this dotted curve by the transmission of the atmosphere. So this is a situation what I call a standard atmosphere, which has a few conditions, and then we have to consider the product of this times this. And then this means that the instantaneous effective passband may vary with the characteristics of the atmosphere. And this is something for which we have a major contribution in France. So why is it so important to have precise photometry? Because we will do cosmology only with photometry. Then the best photometry will give you the best photo Z. So we will have we need the photometry redshift determination, because it's absolutely impossible to make a spectra to spectroscopically measure the 10 to the 10 galaxies, especially with these magnitudes. So here you have an example, the same galaxy which is considered which is put at different redshifts. So here it's from 0.02 to 2.02, and you see here what magnitude you will measure in every of the passbands as a function of the different redshifts that you have. So you see that to measure the redshift, we will have to measure the colors, the magnitude differences between spectra, and to take into account all the possible colors or combinations to extract the photometric redshift. So this is a complete industry that I will not develop on this. If you have questions, we can discuss later. But since LSST is a really big story, I cannot speak a long time on this. So, as I said, we need because of the variability of the atmosphere, we plan to measure the atmospheric transmission with this. So why do we need this? Because I said that we analyze the light from very distant objects, and color is essential. And on the way of the light is redshifted. It also it also has some dust. It can go through intergalactic medium, which is something which is stable, which do not change with the time. But the last 10 kilometers are really critical, because this is the atmosphere and this is variable. And this can be this is especially problematic in the infrared. And the infrared is something critical also for the determination of the photo Z, because it is very sensitive to the water vapor in the atmosphere. So if we are able to measure the atmospheric transmission, then we can compensate for the variability of this transmission and go back to a kind of standard conditions, atmospheric conditions. So this is the mission of the auxiliary telescope. And this is essential, because if it's successful, we will not only improve the photometry, the quality of the photometry, but we will also be able to use even the non-photometric nights, because non-photometric nights are non-photometric because the atmosphere varies. If we are able to measure the variability in real time, then we can really reuse this non-photometric night, which is almost a factor of 2, in fact, in reality. Okay, so every science can benefit from this. So the auxiliary telescope, it's a spectrograph, in fact, and so I will make a long story short, just showing you that we are able to measure the absorption, atmospheric absorption, by using standard stars that are measured out of atmosphere by Hubble Space Telescope or Gaia. Then we do ratios on what we measure on Earth with what is measured out of the atmosphere, and we can deduce the absorption. And this is, we have now, I think, almost 5,000 measurements, because we started already 3 years ago to take data with this telescope. And you can see that the water vapor is really strongly changing. So you have the water vapor, which three bands, ozone, which is not too variable, and the aerosols also, which is another aspect.
So is it supposed to be uniform in the sky?
That's a good question. That's something that we are testing now. We are trying to do with all the quantity of measurements we have. We are trying to see how it is sensitive to the direction in the sky. But our favorite plan would be to monitor the atmosphere in the exact same direction than the LSST in real time, if possible. Okay, sorry. So we extract, for example, an example of the extraction of the water vapor. This is a constantly dry night, and which gives us a good confidence in the precision of the well, this is the precipitable water vapor, so it's measured in millimeters, equivalent of water. So we have a precision of 0.15 millimeters on a scale that goes from 0 to 20, typically. And so this is a slowly decreasing humidity, and this is a strongly changing humidity, so like a non-photometric night. And just here is the air mass of the standard that we use. Is just to show you that our result has to be, but it's a check. It's a basic check. It is independent on the air mass and on the standard. So Vera Rubin is a complete ecosystem. I mean that you go from the observation, from the raw image to so process, archive, and also service for the analysis, which is absolutely complete. So and there is another aspect. So you see that the scale, the data scale, is of the order of the petascale, or petaoctet. So I will not go into the details. There are several. This is the instrument removal instrument. Well, the way to take into account the flat fielding and everything. And there is, I continue on the next one. Yeah. So there is, so you have, so that's typically we will have 20 terabytes per night. And the deliveries will be prompt data products, first at the alerts. So I said that we will have of the order of 10 million alerts per night. These alerts will be delivered within 60 seconds, and they will be delivered to community brokers. That's engines that make selections of the alerts for selecting the physics and selecting the possibility to follow up with other telescopes. We have also a 24-hour process with the process of the image, so that's reduction, instrument removal, and everything, instrument signature removal, and then on the base, which is much longer, we will have the data release, yearly data release, and so voilà, that's the I would say the basic scheme. For example, for the brokers, which are part of the ecosystem, so they are designed to sort all the alerts during each night. While we have 1, 2, 3, 4, 5, 6, 7. We have now seven brokers. So I will just say a few words about the one I know the best, which is Think, because Think has already been used for several years with ZTF data. So with a lot of supernovae discovery, so which means that if you discover a supernova, you can trigger follow-up observations by a lot of partners here, so from South Africa to China and Australia, and so you have many. You have also you can make, for example, searches for microlensing. You have many possibilities, and they have also a series of papers about the detection of asteroids. So you can find a lot of literature on this. So now a few words about the most recent events that happened at LSST. So this is what we did with the commissioning camera. So the commissioning camera is just the central part, was a small sub-camera with one raft, made of one raft, 9 CCDs, which was installed on the telescope, on the main telescope. So we like this, we could have a full rehearsal of the real conditions of the telescope. So here you see, for example, the co-addition of the order about 200 exposures. So the exposures, since the telescope is not equatorial, you can have different rotations of the field with respect to the sky. Then you can here have you have the addition of 200 different orientations, which makes this complicated stellar-like object. And then, so this is the camera. You can maybe guess the 9 CCDs. Now this is the cumulative image, and this gives you I would say the 5 sigma limiting magnitude as a function of the position, and the central part is the one that we can go the farther in magnitude because it's the most exposed one. So this is more or less the same, but with only 20 measurements, and it's just to show you that. As expected, the photometric uncertainty as a function of the magnitude for the four filters. Not all the filters were used in the LSST-COM. So you can just see that if you increase the number of exposure you decrease the uncertainty and the magnitude, to decrease the magnitude error. Okay, that's something which was expected, but that was important to test. Now that's the very first result from the LSST cam. So that's the complete camera here. So as you know, the first light on the sky was taken on the 15th of April of this year. What I showed before was the process of a series of images that was shown to the public in the 23rd of June. But the first light was in 15th of April. And since that time, this is a summary which is from the last week. 30 September. This is the visits that have already been done with this camera, the camera, and this is a science validation survey. It's not yet officially the official survey. And so this you show here the distribution of the science visits filter by filter. So that's a distribution. Yeah, that's as a function of the nights for each filter. So you see that in some nights we have more than 750 images taken during the same night. And the objective is a little bit more than, it's typically 800. Now it depends on the season also. Yeah, it was winter, so you have more images. But the price to pay in winter is the storms. So that's why what explains some of the holes here. There have been at least 2 or 3 big storms during this winter, in the mean winter in the south hemisphere, and that well, okay. So at that time, the observatory is closed, and nobody can stay on the mountain. So it takes a few days to restart. So so this is some results from the validation survey. This is not the best news I can show you. That's the distribution of the full width F maximum. So that's the PSF, the experimental PSF, which you remember that the site is supposed to have an average of 0.65 arcsecond. Here, 0.65 arcsecond is just not it's probably it happened only one time. So there is some work to be done here. There is probably some work to do on the dome also. That's one of the most complicated improvement to do in the next few months. So this is also, as I showed before, this is the maximum magnitude that can be reached as a function. Well, that's the distribution of the maximum magnitude that is reached for the different filters. So no surprise here also. And so that's for the wide field survey. We have some deep drilling fields which represent that and will represent also for the survey about 7% of the time, and between 1 and 3% of the time will be devoted to small field survey visits. You have a list here, so that's very specific targets that have to be also wide targets to take the benefit from the wide field of the LSST. And there is a target of opportunity. I will say a few words about this. That should be represent about 3% of the time. Okay, I have a few minutes. Preliminary, the performance that I can just show you is this. Readout, I said 3 seconds, with a few electron noise in the readout system. So we are not limited by the electronic noise. We are always in photometry, as usual, limited by the sky background, Poisson noise. The filter change takes less than 2 minutes, on average 1 minute 30 seconds. It's not at the maximum now, but it's decreasing also. The best PSF is 0.7, but this is all across all the focal plane, not at the center. It's the same PSF on all the focal plane, which is one of the most important aspects of the LSST. You need to have the best PSF on a wide field. So, and we estimate that the typical system contribution is about 0.6 arcsecond. So the 0 points, for those who are not familiar with this, that's just a magnitude that gives 1 ADU per second. So it's between 26.55 and 28.56. We have 1 CCD which does not respond, which is dead. That's probably due to a short circuit with dust of copper. It's not completely clear, but there is somewhere a short circuit. But that's good. That's very good. And 188 over 189 are fully operational. So the maximum number of visits at the moment is a little bit more than 750. And the science validation surveys is on its way to finish. Now, well, it's not always, it's not completely finished. For the Oxtel that I mentioned before, auxiliary telescope, we are now in a mode of just push button. It's now, because it has 3 years of experience, so it's now completely automatized. So there is no need for additional staff for this, which is important also. Okay, so a few words about the first result that probably maybe you saw. That's about the asteroids. That's very easy to have very fast results on this domain. So the Rubin Observatory just found more than 2,000 asteroids just in a few days. So this is for the press release, more or less, and this is for scientists. So this you see in a small region, 6.5 arc-minute square. You see some of the bright asteroids, and the segments here. The color of the segments represent the filter that has been used to take the picture. So then you can see that they are perfectly rectilinear, aligned, and you have also in several colors, which is something important for the study of asteroids. So I know that it's not cosmology, but we don't have already the results on cosmology. So this is the distribution of the small bodies in one of the field M49. So you have here the ecliptic here. So that's, you have an inclination also of these small bodies, and this you have a few light curves which shows the rotation of the object. So you see the object with variable orientations. Then you see a reflection which is moving, which is changing, and we have very quick, very fast moving of I think 0.2 hours. So you fold the light curves, and with much longer ones. So that's just a way to know the spin of the asteroids. And also here you have the distribution of the ellipticity here, and the inclination with respect to the 5 minutes. Okay, I have almost finished. And inclination with respect to the ecliptic. And here at this large distance, you see a few trans-Neptunian objects. So this is published. Okay, I'll say now, well, with the LSST catalog, we will do basically all astrophysics. So LSST was built for this part of physics, so for the cosmology. Though I have to say a few words on this. So the main deliverable will be this large catalog, which is what I call a kind of 4-dimensional object mapping. So stars and galaxies, but galaxies is the most important for us, with positions, photometric redshifts, and also time variations. And the other mode of survey will be 20% of time, as I said before. So the time domain will be very wide. The most interesting from cosmology will be the supernovae, GRBs also, and also gravitational waves, optical counterparts. Also we have also, this is one of the only domain where LSST will be able to work in a target of opportunity mode. So I see here we have already seen, though, and we can make also a lot of science with the mapping the Milky Way, and for the dark energy and dark matter, we will one of the main subjects will be gravitational lensing, supernovae clearly, and large-scale structures. So this is the high-level science requirements. What I showed before was just something not really elaborated for the high-level science. So we will have a survey on about half of the sky with 825 visits after the end of the survey, after 10 years. So in 6 filters, each visit is a 30-second exposure. And so that's the magnitude that we can reach in a single visit. And after the 10 years, after co-addition, this is the magnitude that we can reach in the catalog. And what we hope with the photometric calibration is to go lower than 5 millimag. We hope to go to 1 or 2 millimag. So depending on the effectiveness of the corrections we do with the atmospheric corrections. Okay. So transient. So a few words about transient. I already spoke about transient. I can make so that's linked with the brokers in general. I can make so just one thing that don't forget also we are also able to show variations on large structures like supernovae echoes, and so here I will just say a few words about the search for the. Okay, so no, this has skipped. Yeah, the search for electromagnetic emission associated with gravitational waves. So this is the circle. This is the annulus that are allowed by the different antennas for the gravitational waves. So these antennas are able to give typically 20 square degree box, and then in 20 square degree box, if you assume that we have this precision, we can cover this with only 3 LSST fields. So in this situation, from the time we have the alert from the gravitational waves, it takes 40 seconds, I just said on average, to point toward the correct direction. Then we take three double exposures, and in total you take in 214 seconds you can have all the information. Yeah. Then you have to select to find. And then at the end you expect only 10 brand new variable objects after the selection, and 10 new supernovae typically. And in these 10 objects, if you have other telescopes that point to these 10 objects, it starts to be reasonable to follow up only 10 objects. All right. Okay. Thank you very much. That's the conclusion.
I'll not show you a noise.